Oh. Hello, all the presenters. Please turn on your video and unmute your microphone. And our moderator, Mr. Jayaraman Durai.
Hello, Jinwai.
Yes, yes, thank you. Let me see. Professor Zhuo is here. And Luis Felipe, can we see your face?
Oh, I am here.
Okay. 这是路易斯，Felipe. Hello, Luis.
Yes, I am here. Can you see me? Can you hear me?
Yeah, we saw you. David Trujillo. David, are you there?
I'm here.
Okay, so we're ready to start, Durai.
Yeah, thank you, Jinwai. Participants from different time zones. We welcome you all for today's webinar session. As you know, bamboo is one of kind throughout the world's tropical and subtropical region. So it was widely used for different forms of construction in the rural settings. Due to increasing population, about 1.6 billion people live in inadequate housing, and the housing infrastructure sector also contributes to climate change due to the use of high carbon intense concrete, aluminum, and glass, high strength and overweight. But it is also beautiful, elegant. It is an annual yield property similar to the hardwood. It is earthquake and disaster resistant. It is economical, available. However, it is still considered as a poor man's timber. In the past 2 to 3 decades, with technology development and innovations and engineered bamboo products for indoor and outdoor applications, such as beams, panels, floors, veneer products, cladding applications are a key element for the bamboo sector development. Minbar's webinar under this theme, Bamboo, a suitable construction material, aims at generating awareness and share knowledge on potential of bamboo to alleviate housing. Under the theme, bamboo as a suitable construction material, we have some 5 sessions, 3 sessions of the round poles, and the 2 sessions focus on the architectural and the structural use. One under this theme focused on showcasing the architectures of the bamboo culms, and the current session is a continuation of the previous session. Previous session focused on the analytical technique, joinery aspects of bamboo, design elements, and preservation and the treatment. In continuation to the previous session, a bamboo spatial lattice structure in China, OCA's disaster resilient housing in Philippines, and on standards and codes for the wider application. Today's first presenter is Professor Zhuo. He is currently an associate professor in the College of Civil Research, experience in spatial steel structures, especially for construction mechanics analysis, focusing on the raw bamboo spatial grid structural systems. He is currently the project lead of the RAW organization. The multi-culm bamboo spatial lattice structures, which was invented, has been successfully applied in China. Please continue, sir.
Hello.
Please.
Fantastic. Good morning, good afternoon, and good evening, everybody. I'm very honored to share with the recent research and practice of my team on raw bamboo structures. Oh, no. Wait a minute.
卓老师，您重新分享一下，选择您的 PPT 的那个本身，别选择桌面。可能
你现在看到的是那个是我的 PPT 吗？
现在看到的是吧？是桌面。
Bamboo is an elegant, ecological, and cheap building material. The culm mechanics property are directional, with a higher excess strength compared to mined steel, but weak in the traversing directions due to the geometric characteristic and in the thin wall, irregularly cross-section, and longitudinal direction. Neither can we change the diameter and thickness of culms. The main advanced technologies in timber structures are not suitable for bamboo structures. Joint is the key for the structure performance. There are dozens of bamboo culms joints in the world. Traditional joints use the nail, rope, and other material. For example, fishmouth joints or the weakened buried capacity of the joint. New connection depends on friction. The connection performance between bamboo and nail is variable under different environments. Lashing is the most common used traditional joint in the world. In the past decade, many modern joints have been invented by researchers from various countries. These joints made of concrete, metal, grout, and other materials. Many of them are suitable for special structures. Modern types of bamboo joints have made a great progress in the foundation and the connect performance. However, the price of modern joints are generally high. The cost is very high, and some are even dozens of times higher than bamboo itself. Now, we have mentioned most of the present joints. Although they are different in materials or forms, they have one thing in common. They are all followed the relationship of line-line connection, which is written in the textbook of structural mechanics. Let's let's talk about the spatial structures. First, each joint connects many members at different spatial angles, which makes manufacture as well as assembling quite difficult. Second, in spatial structures, almost every joint is different from the other joints, which makes manufacture and assembling even more difficult. In bamboo structure, the main cost is spent on two things. One, the production of this complex multiple direction joint. Two, the connection between joint and its corresponding members. Higher cost has unfavorable to application. The public would rather choose wood, which is also a renewable material, than the troublesome bamboo to build a house. Next, I'll introduce what my team has done. In my opinion, in engineering application, the simple, the better. The simple, it means simple joint, simple equipment, simple operation. The better means low cost and good performance. For the objective are achieved, simple manufacture, convenient assembly, low cost, and reliable performance. 4 years ago, I invented a new type of joint named double ring crab, and the new type of bamboo spatial structures named multi-culm bamboo spatial lattice structure. A ring crab is formed by two similarly with two legs on both sides. When each leg drills a hole, a pair of double ring crab is composed of two ring crab.
Y mamita, yo le aviso, los papás también dicen que no se conectaban.
And they connected through a common bolt in the middle legged hole. This double ring crab could be used not only in end connection, but also in parallel connection for two neighborhood bamboo culms. The crab tangent two neighbor culms with three bottom. Three pairs of double ring crab connect three culms, and together they formed the culm triangle. A pair of double ring crab connect two different R1 and R2 that corresponds to two culms. If the distance D1 equal D2, it's easy for manufacture. No matter how different between this nearby the culms, the access position of these bamboo culms will not be affected either to end connection or to parallel connection. This function is very helpful to control assembly accuracy. The And the next invention, a new type of structural system. And bamboo culm looks this the photo. A bamboo culm triangle is formed by connecting the end of 3 bamboo culms each other. Multi-culm bamboo spatial structures is formed by connected neighborhood triangles in parallel. If each triangle is connected the top triangle in parallel, the stiffness and the bearing capacity of the eliminated multi-culm bamboo spatial lattice structure can be strengthened. Let's watch the video. It's a single layer. It's a double layer. The stiffness and is very well. And I want to explain how to extend longevity for structure. Please watch this video.
Zhuo老师，我们大家看不到 video。
看不到 video。
哦，
那我要么待会儿再放。哎呦，这个怎么退出？是放这里吗？After engineering application. After about 3 years of experimental and theoretical research, we have carried out engineering practice last year. The first engineering application project located in Beijing. The complex theory surface was divided into 9 type size triangles. The cutting. The culms was cut according to the design legs, and the 2 ends of each culm were cut according to the designed angle. Connect. After the culm had been grouped, the corner of each angle was temporarily fixed with tape. And then semi-mortar was injected into the corner. We chose the install method, which was formed the center with the center to its edge. The whole structure can be completed simply with the help of tripod and a hand chair host. No scaffold was needed. It takes 1 day to build the structures, and the installation of the internal and external decoration leg was also complete in 1 day. Case 2 is the pavilion moved from the indoor to the outdoor, and the block installation method was used. And the application case 3 was in Sichuan province. The base size of the case 3 is the same as case 1. The form is similar to case 1, but I increased the base to investigate the stiffness of its elegant structures. The two structures the case 4 is in Xi'an. It's a dome. The finished structures had a good stiffness. Conclusion, the feasibility of the invention could be proved by the series of successful engineering practice. The development and popularization of new structure system needs the support of design theory, which will gradually establish on the basis of the large number tests and engineering practice. Thank you for your listening.
So many thanks, Professor Zhuo for providing us an overview of the joinery types available in the bamboo construction, and also providing an innovative multi-culm in the bamboo spatial artist structure. So as we know, triangle is like one of the stable forms available in construction innovation, and it has like some wide application. And it also eliminates the structure is in form of components and in form of triangles. It also provides a scope for prefabrication, front commoditized bamboo house, and it is also possible to scale it out. So many thanks for your presentation. Now we can move to our second speaker, who is like Mr. Luis Felipe Opus. He is the head of technology at Pace Baha'i Foundation in the Philippines, and he is also the director of the Pace Baha'i Innovation Center, which is a laboratory for sustainable construction system. He is also the part of, he was also part of the committee that created the Bahar Q building code in 2002, and including it into the bamboo structural code of the Colombian National Building Code, NSR 10. Luis Felipe is also a member of the ISO Technical Committee 165, and then like working group 12 representing Colombia. His topic and his presentation is on the research in the Philippines, and for income families. Always Philippine Opus, please proceed, sir. Your mic, like we couldn't hear you.
Thank you. Now, for Imbar to having me here today, and I want to share all the experience working here in the Philippines. So now I will share my screen. So I hope you can see now. So let's start it. So my presentation for today is about bamboo research in the Philippines, but it's a little more extensive than that, because also we need to talk about the context of this research and why are we doing bamboo research in the Philippines. So let's start talking why it's important to research about bamboo in the Philippines. So Philippines is a country located in the Southeast Asia region, and there is 110 millions of inhabitants in this country, and more or less 25% of the population lives under the line of poverty. So there is a big demand for housing in this population, and also a high deficit in housing in this country. At the same time, in the country, we have an average of 20 typhoons per year. Actually, this year, already 21 typhoons touched land in the country and making big disaster. We just see Typhoon Bamko last weekend and the flooding in the whole country. And 1 week before, we have a Typhoon Rolly also devastating parts of Bicol area. And 1 week before, another one. So it's like, and typhoon season is one after the other every week. So at the same time, Philippines is located in the ring of fire of the Pacific Ocean. So we have earthquakes, tsunamis, volcanoes. So all the possible natural disasters are here in the country. So there is a lot of work to do in structural engineering, but also trying to find solutions for housing that is affordable, but at the same time resistant. So this story started in 2011 when a German engineer was working in her master thesis. Her name was Corinna Salzer. She was doing her research here in the country, supported by Hilti Foundation, exploring possibilities to work with natural and local materials for social housing here in the country. So in 2012, Hilti Foundation contacted me, and I was working as a consultant together with Professor David Trujillo, and we were supporting the research here in the country. In 2014, Hilti Foundation decided to create Best Baha'i Foundation in the Philippines. I moved to the country, and we started to work in research more deeply, but at the same time building homes in the whole country. 2015, we complete our first 3 projects. In 2016, we get our ITEC accreditation. That is an accreditation that allows us to get building permits in the country. So Best Baha'i is a Philippine NGO fully supported by Hilti Foundation. And our objective is to provide alternative building technologies that enable us to build houses that are affordable, resilient, and resistant, and eco-friendly for the more poor people in the Philippines. So our technology is based, but not copy, I want to clarify, from the bahareque, cemented bareque or bareque cementado from Colombia. But we need to understand that in South America, especially, there is no typhoons. So the structures are more designed for earthquake resistant, not for typhoon resistant. So in the beginning, we took some components of the bareque technology from Colombia, and especially because at that time, the bareque technology was already included in the building code in Colombia. So that help us a lot because it's a system that is already normalized. Even other countries like Ecuador and Peru already include this technology in their building codes. So we take that technology as an started, but we have to improve a lot of connection systems and reinforce more the construction to resist the strong winds and the uplift during the typhoons. So And at this point, I just want to clarify that when we are talking about bajareke or cement bamboo frame technology, is how we call it here in the Philippines, we are not talking about this kind of bamboo structures that I'm showing you, all of you, at this moment in the screen. These are more like three-dimensional trusses of space trusses that are very common and the work of Simon Veles, for example, or other architects around the world. Beautiful structures where the bamboo is the main structural component, but in the system that we're working here, and you will see in the coming slides, we are working more in a system like a shear wall or a structural wall system, where the walls are the structure of the construction. That means they're responsible to resist vertical loads and horizontal loads. So this technology, as I mentioned, was originated in the 18th century in the coffee region of Colombia. So here just some samples of the construction techniques that were used at that time. So you can see that even 3-story, 4-story buildings were normal at that time. And the system is just a frame made of bamboo, sometimes with timber, using flattened bamboo as support for the plaster, and a cement plaster once the cement was available. And before that, the people use lime with some animal excrement. So in 2002, Colombia introduced the system in the building code. So giving formulas and a process to analyze those structures. Example of the system used in Colombia, so already the normalized one. This was part of the reconstruction project of a city that was devastated by an earthquake in 1999. So this project was executed in 2002 by the SICMIC Engineering Association of Colombian Engineers in Colombia. So 80 houses built with this system. So coming to the Philippines in 2012, we decided to use the Bareque system as a base. So, but the species of bamboo in the country is completely different from the species that we have in Colombia. In Colombia, normally you find Wadua angustifolia kunt, but here in the Philippines, the most common bamboo is called Bambusa blumeana, or the local name is Kawayantinik. So the first task was to determine the mechanical properties of the Bambusa blumeana and also the resistance to conventional connections with using bolts and even plus mortar cement inside the internodes to check the resistance. So we make tests for mechanical properties, connections, and walls. So here's some pictures of the tests that we are doing. So you can see here, these are new pictures. These are not from 2012. These are from this year in our new laboratory that I will show you. So, but for the test that we did in 2012, we used the ISO 22157, the last version, the previous version, sorry. And here's some data of the results that we got at that time. So we get results for compression parallel with characteristic value of 20 megapascals, shear parallel 4.1 megapascals, tension parallel 97 megapascals, tension perpendicular 0.53, bending 53 megapascals, and modulus of elasticity as well, 17 gigapascals. Also, we make some tests for Dendrocalamus asper of giant bamboo that grows very well here, especially in the south part of the country, in the Mindanao Island region. So we have already conducted some tests like compression parallel, shear parallel, and tension perpendicular. So we get a characteristic value of 43.7 for compression parallel, shear parallel 6.3, and tension perpendicular 0.33. So we still are making tests for this bamboo. So in coming days, we are testing the bending and the rest of the properties. Here's some images of our testing connections, embedment of bolts in bamboo culms, and also connections already created with bolts and full with mortar. As well, we test walls, shear walls, starting from just the frame, adding the bamboo mats and the plaster. So we test different kind of matrix like flattened bamboo, ribbed lat mesh, chicken wire mesh, and using cement plaster also to check the resistance. Internationally, we also conduct some tests in Indonesia for shear walls using Indonesian bamboo species. We make this together with the Bandung Technology University, ITB. There we make some tests also for shear walls and mechanical properties of Indonesian species. And even in Indonesia, also with the ITB University, Bandung Technology University, we made some tests for fire resistance. So we use the ISO 834-1 to determine the resistance of the bamboo walls against the fire. You will think, but bamboo is a flammable product, the resistance will be very bad. But no, in this case, we test the wall with double cladding. So using plaster cement in both sides. You can see here the wall. This is the wall that was tested. The wall is completely plaster. So you see here the wall after the test, and this is the destroy cement that we need to open to see the condition of the bamboos after the test. The test was conducted for 1 hour following the ISO curve of temperature. And here in this graphic, you can see the increase of the temperature in the other side of the fire. So you can see incredibly good. One big question about the research about the system, if we can use it here in the country, is if these construction houses can resist typhoons or not. Because as I mentioned before, in Colombia, where the system were originated, we don't have typhoons or hurricanes. Only the north part of the country in the Caribbean Sea can be hit by typhoons, but in the central part of the country, there is not this kind of natural events. So we decided to make a test with 3 full-scale houses that we built in a province called Bicol, in a town called Guinobatan. So you can see here part of the Luzon Island and the Bicol province, and this yellow pin is the location of the houses. So why we choose this location, typhoon with winds more than 220 kilometers per hour. So we built these 3 houses. We install some weather station, a satellite weather station, where we can monitor the wind speed, and we just wait for the typhoon. These houses were built in 2013, and in 2014, around 6-7 months after we finished the houses, we have the first typhoon hitting these houses. It was Typhoon Glenda. It was a super typhoon, category 5, and we were recording the wind speed during the event. So after a few days that we were able to reach this place and take this picture, you can see the condition of the house is good. The house don't suffer any damage. Only this small broken GI roof that you cannot blame the system. Is actually a problem of the how the roof was fixed to the structure, but in any case, there is not a damage that compromised the stability of the house. But the other interesting fact about this picture is that there is not any more weather station, because the weather station collapsed during the typhoon, and the last record was 185 kilometers per hour. We get records from other weather stations around in other locations with wind speeds up to 220 kilometers per hour. And unfortunately, the traditional construction method that use very poor technology in the connections, using wire and things like that, and it's not any connection to foundation, cannot resist those kind of winds. So you can see here the collapse traditional Nipaha. So at the end, we developed this system that is typhoon resistant, earthquake resistant, fire resistant, and insect resistance, because we treat all our bamboo poles with a very good treatment method that allow us to be sure that the insects will not eat the bamboos. I don't speak more about treatment because I know Sebastian was talking about that in the last presentations. So here you can see more in detail the components of the house. So starting from top to the bottom, we have a roofing system using any commercial material. You can use galvanized iron sheets, you can use clay tiles, you can use shingles, asphalt shingles, whatever you want to use is compatible with this system. And supporting that, you have a kind of a truss or frame system in the roof using purlins and rafters. But for that, we use always bamboo and sometimes a combination of bamboo and wood. And the structural main system is a shear wall system made of frames of bamboo. We call it cement bamboo frame system or cement bamboo frame technology. And we use studs made of bamboo, horizontal elements made of timber to avoid the use of fish mouth connections. So that allow us to prefabricate the walls very easily and reduce the cost of the house. And when you are building social houses, every single peso, in this case, because peso is the money in the Philippines, every single peso that you save is money for the next house. So we need to be very careful in the cost of these houses. And at the end, you have a concrete foundation, conventional foundation using footing beams and concrete slab. As I mentioned also before, we get in 2016 the ITEC accreditation. This is an accreditation given by the National Housing Authority here in the Philippines. And with this ITEC accreditation, we are able to build these houses legally and getting building permits, even if the system is not yet included in the building code. So we have to prove the National Housing Authority that our system is safe, is a good alternative for social housing construction, but especially we need to guarantee that the houses will not fly in the next typhoon or will collapse in the next earthquake. So we need to show them all the proofs of the test that we did. So I don't want to go with this because you already know why bamboo is good. It's a sustainable harvesting and good income material. It's a strong, grows so fast, and the carbon footprint of a bamboo house will be always less than a concrete of a steel house. So one thing that we had to do here in the Philippines when we arrived was to create all the value chain for the bamboo. It's true that the country is full of bamboo everywhere, but there's not an industry of the production of bamboo. So we need to develop a value chain with the people of Best Baha'i, the team that make an incredible job. They all work very hard to create these facilities together with other partners around the country. So we have a team of local engineers. And actually, I want to clarify, I'm the only foreigner in base. All the team is Filipino, and they work so hard to make all these things happen. So they go to the provinces, they work with local farmers, and they create these facilities. They help them to build it, and they can process. So right now we have a capacity installed for a production of something between 8,000 to 10,000 pieces of bamboo per month. So unfortunately, during this year, the production is very low because the pandemic hit Philippines very hard. So these are some of the model houses that we are building in the country. So we have 2-story houses, we have duplex houses, bungalows, and even row houses until 4 houses all connected. Some of our projects, we are almost in the whole country. We are soon starting a project in Mindanao. That was the last province that we don't where we don't yet we're building. So we are starting a project in January, 50 houses in Bukidnon province in Mindanao. Until now, we have already built 800 homes, giving shelter to more than 3,000 Filipinos, creating direct jobs, saving a lot of carbon. More than 10 communities built in the country. And aside of that, we started our first international project this year in Nepal. It's a project together with, completely supported by Hilti Foundation, but with all the technical support from Best Baha'i, and implemented partner there of the main partner in the country is Habitat for Humanity. So during this year, even during the pandemic, we were building 34 homes in the province of Japa in Nepal. And Hilti Foundation already approves 50 houses for the next year in Nepal. with these communities, we also work in building communities for social work or even for livelihood projects. So aside of all these social projects, last year, Best Baha'i together with Hilti Foundation decide that we want to go one step forward and create the Best Baha'i Innovation Center. That is a laboratory that focuses in the research of sustainable materials, giving emphasis in bamboo construction, of course, but open to other materials like wood and whatever is new in the market. So we said this facility is a small laboratory, but the interesting is that we are focused in bamboo, so we can make a lot of tests. And right now we have a universal testing machine where we can determine mechanical properties. We are finalizing the setup of our reaction frame where we can test more walls. And also we have an area where we can make a full-scale construction models. So like here in the right side of the picture, you can see we have a full-scale house where we can test new components, or we can train people to build with this technology. The Innovation Center right now is making some agreements with international organizations or universities to promote the research of bamboo. Of course, our main donor and partner is Hilti Foundation. Our main partner locally here in the Philippines is the La Salle University. With them, we were working already for more than 3 years doing research. And we are signing some MOUs with international universities like Coventry University, Mara from UK, Mara University from Malaysia, and we have 3 agreements under negotiation, one with the Hong Kong University of Science and Technology, another with Pittsburgh University, and the last one with Universidad del Valle from Colombia. And aside of the universities, we are also working in research with ARUP, together with Sebastian Kaminski, that is part of this forum also. So we want to create like a network of institutions that wants to promote the use of bamboo, and also help students that also believe in this technology and support them in research in their countries, but also helping the people that wants to work with bamboo here in the Philippines. So we want to create knowledge that can be used for building codes, and also to improve technology and reduce costs of construction with bamboo, making the system more competitive in the future. So that is a very short presentation about what is Best Baha'i doing in the country, but also what kind of research are we doing in the country. So I invite all of you to follow us in our social media, and you are welcome to visit us here in our Innovation Center in the Philippines. Thank you very much.
Okay, yeah, thank you very much, always Philip, for your interesting presentation. And to introduce our participants about bar technique, like which is like very popular in the countries, and construction techniques, even though it is traditional, it is like quite good constructing like bioclimatic houses, and it is also like fire resistant, like thermal resistant, and other properties as well. And it is quite clear from your presenter. And as you said, in like the Philippines, you tried in the typhoon areas, and then in India, I think like some few of our partners, the Konkan Bamboo and Development Center and other organizations, they have been constructing this like river. So it is like some quite clear that like some bamboo is good material for the disaster like resilience. And the another important point from your presentation is to identify the species for construction. It is also quite important. Even though we have around like some 1,600 species of bamboo, but the species used for construction is like some only few. As you said, in Colombia, you have the Godo angustifolia, and in China, they use like some Phylostachys in like so many cases, and in Philippines they use like some Bambusa blumiana or aspa, and in India they use like some Bambusa balqua, and in Africa they use like Ashania alpina. So I think for the interest of the participants has to be clear on the species which they want to use for the construction. And in addition to the species, the age of the bamboo selected for the use as a structural material is like very important. Probably Sebastian would have cleared it yesterday, but I wanted to say it again today for the interest of the participant who hasn't attended the previous session. The species, the age, and when we treat bamboo, since like bamboo is a biological material, it is prone to attack by insect, fungus, and like some mold. So treating it solves the problem, and then which makes the starch inedible, and then the bamboo can survive as any wood or the steel structures can survive. So thank you very much for clearing the whole concept together in your one presentation. So now we can go to the third presenter and the final one. Dr. David Fajello is an assistant professor. Okay, I am sorry. Before I move into introducing the final presenter, I want to request all the participants to fill in the registration form. Online registration form, I am posting it on the group chat box. Please click the link and then please fill in the form so that we can connect you again for another webinar or for other connectivities. So sorry again. Now we move on to the final presenter, which is David Fajello. He is an assistant professor in the civil engineering department at Coventry University, and he is also the chair of the INBART task force on the bamboo construction. He has been researching, teaching, and promoting bamboo for over 20 years. He has authored over 25 bamboo-related publications. David was the project leader for 2 ISO standards for bamboo, ISO 22157 and ISO 19624. He is also actively participating in the revision of ISO standard 22156, which relates to the structural design of the bamboo construction, and chapter G, which relates to the timber and the bamboo structure of Colombia's building code. David is a chartered member of the Institution of Structural Engineers and a member of the Colombia's Earthquake Engineering Association. His presentation identifies the state of art of the bamboo engineering, including the significant progress made in the development of standards and codes related to the bamboo round pole construction. So I welcome David Fajello to give his presentation. Please, sir.
Thank you, Durai, and thank you everyone in the team in INBAR across the world. And thank you to the audience for joining us today in listening to this presentation. Let's see, well, firstly, let's see if this presents properly. Yep, can everyone see this properly? Excellent, so let's move on. Good.
Okay, correcto.
The title of my presentation is Making Bamboo a Mainstream Structural Material. So what do we mean by mainstream or conventional material? So here I've come up with a list of what could be some possible characteristics. One of them, that the material is readily available. It is available in the market through a reputable and trustworthy supply chain. And Luis Felipe showed us about how important it was to set up a supply chain. Reliable We need a material that has mechanical and physical properties that can be relied upon. It needs to be well understood, so most structural engineers and other building professionals know how to use it, and there is a consensus of how it can and should be used. And legal to use. We have national legislation as well as codes and standards that support its use. So in my mind, these are the characteristics of what would be a conventional or mainstream material. You might think of some more, and I'd be really keen to hear what your suggestions are. So we need codes and standards to ensure that we have a reputable and trustworthy supply chain. We need codes and standards to help us ensure that the material has mechanical and physical properties that can be relied upon, and codes and standards that help us to know how to use the material. And hopefully those codes and standards reflect a consensus of how or should it be used. So throughout the 21st century, we have had a gradual process of development of standards and codes across the world. Interestingly, the first one was actually from California, but it's a very simple document, and it doesn't provide you any details of any species, mechanical properties, how to design a beam or column, a connection, a shear wall, or any grading. All it tells you is how to derive some design values. Luis Felipe earlier then mentioned that in 2002, there was a design standard that told you how to design some elements, primarily was shear walls of the Bareque system, and it had a very, very simple procedure to design columns. It also had some guidance about how to build connections, not how to design them, and some guidance of how you should grade bamboo. As we move forward, I think one important breakthrough, a very important code, was the NSR 10 from Colombia, which, as you can see from this chart, it ticked many boxes. It only was for one species, but it stated the mechanical properties for it. It told you how you could derive the values, how to design beams, columns, connections, shear walls, and it had some guidance on how to grade the material. There has since been several developments in Peru. There's an Andean standard in Ecuador, in Mexico, and I might be skipping something from somewhere else in the world. And but I think, in our opinion, the significant breakthrough will be coming in next year with ISO 22156, because it ticks directly or indirectly all the boxes. It doesn't specify any species, but you can find the mechanical properties through using ISO 22157. And it is accompanied by a full grading standard, which is ISO 19624. So here is a sort of 3 recently developed ISO standards around the use of bamboo culms. And this is the one that we're expecting next year to be released. So a bit about the journey of how we got to these standards. So we have ISO Technical Committee 165, is a committee where the original ISO standards that were written about bamboo in 2004 were developed. In 2013, we feel that it's important to reactivate our presence as INBAR in the ISO Technical Committee 165. And so at that meeting, working group 12 is created, bamboo structures. In January 2015, we also felt it was important to have a task force that supported the development of these standards and other activities as I mentioned, we have 2 ISO standards that have already been published. One of them is a revision from the original 2004 version, and we have coming soon ISO 22156, which we expect will be published in 2021. We're also starting to tackle the technical committee visited Colombia for the, which was a very memorable meeting. And here we are visiting bamboo structure in Colombia. So in ISO TC165, there is sort of a philosophy of a family of standards where all the standards should be allocated. So either they fit into product specification, material testing, determination of characteristic or design values, and structural design. So we see that ISO 19624 sort of fits here. The grading of bamboo culms sort of fits here in product specification. ISO 22157 sits here more or less in material testing. And one of the things that we ensured is that both standards were sort of harmonized. So that means that they cross-reference each other. However, some of these standards, we felt we didn't have to reinvent the wheel. And so what we've decided to do is that we're not going to always just put the word bamboo in front of some standards when we can use timber standards for that purpose. For example, this one is just a determination of characteristic values. It's just a statistical process. We don't see why it needs to be significantly different between timber and bamboo. So what we've decided to do is to harmonize with a lot of timber standards. We've decided to harmonize across standards. Hello, sorry, someone's talking. So we've decided to harmonize across standards. And so, for example, ISO 19624 makes reference to 12122. And we've done a similar sort of situation with the standard that will be released next year, ISO 22156. It is linked to ISO 19624 as well as 22157, and to many other ISO standards that we're borrowing concepts from to feed ISO 22156. So let me tell you a bit about what we've done in these standards. ISO 22157, what we have basically done is we took a good look at the existing standards and tests, and we introduced some new tests. As I mentioned, we harmonized with ISO 19624, but we also harmonized it with a timber standard for testing in timber so that they follow a similar format. And we've also ensured that we have permissive test methods, and that is that we understand that not all lab facilities are first class. So you might have some lab facilities that are not so good, and so how can you adapt the test to those lab facilities? In the introduced tests, we introduced the edge bearing test, shown here, and we have introduced the split pin test, shown here. Both of these tests are referring very much to the properties of the matrix of the bamboo more than to the fibers, which sort of relates to the work that with Kent Harry's presentation on this subject. In terms of grading, prior to ISO 19624, grading was a fairly simple procedure across the world in standards. Generally, what you find in codes and standards across the world is that they'll have some requirements to check what the species, what the taper, what the bow, what the fissures, what the rot, what insect damage and maturity level are tolerated. And if it complies with everything, you just say it's structural grade. And if not, it's rejected. There is an exception, which is quite an interesting exception, is India's NBC from 2004. It has a range of diameters and requirements for modulus of elasticity and so forth, but it's not very clear about exactly how it works. It's just got, I've summarized the two tables that it contains, and this is what you get if you merge the two tables. One interesting concept about this standard is that it grades by diameter of bamboo. It suggests that you could grade by diameter of bamboo, and it's a really interesting idea that we will come back to later on.
Common challenges.
As I mentioned,
Thinking as
ISO
though university as an example
19624 is a brand new standard that was published in 2018. What does it cover? It has definitions, it has visual grading, it has machine grading, it has something called initial evaluation, and it even provides an example of how grading could work. It has some characteristics. It's not mostly prescriptive about grading procedures. It's not prescriptive how you have to grade. It's simply a framework of how you could create a grading procedure. It creates an option for capacity or strength grading. So we introduce a concept that's not common in timber, but we felt is more appropriate for bamboo, and we'll be discussing later on this, which is capacity grading instead of strength grading. We have the option of visual, machine, or hybrid grading, and it tells you what geometric properties to be assessed during grading. So in terms of visual grading, it's a fairly straightforward process, as you can imagine. We have something called condition properties, which is insect or fungal damage, the presence of fissures, or what we've called longitudinal indentation, which is also like a fissure but towards inside. We have requested that people check diameter, wall thickness. You might want to consider internode length if that is relevant to you. You might want to consider what the lengths of specimens you want to grade around. You might want to check external and internal taper, bow, and ovality. And we've also mentioned other things you might want to consider during grading, which is moisture content and age at harvesting. How could it work? It could be very similar to what I described earlier. You could just say, okay, let's check the condition properties, taper, bow, and ovality. If it passes all, then you accept it. If not, you reject it. So you say this is bamboo of structural quality. Then you might want to add another step, which is that you grade by diameter. And so you might want to check the diameter or maybe the wall thickness, and you assign it to a grade. You might want to assign it to another grade or reject at this stage. One of the things that is new, that is not contained in any code or standard of bamboo that I know of, is that we have something where ISO 19624 is prescriptive about. One of them is the process of creating grading rules for visual grading. It is prescriptive about how you go about sampling. It is prescriptive about the determination of mechanical properties and the requirement of something called periodic evaluation. ISO 19624 creates some grades. It provides an example. So it says you don't have to use this, but this could be an example of how you could grade. Say, for example, on the basis of diameter. And so it says these could be the grades. And then in the case of visual grading, then it says you could create a table that looks something like this, with some properties being determined experimentally during the initial evaluation, and some may be borrowed from other tests of the same species that you believe are relevant, but you are slightly more conservative about. And this is what visual grading with control for diameter could look like. So you measure the diameter and you then sort them here into sizes. Current machine grading of bamboo culms around the world, well, I don't think anyone is doing machine grading around the world of bamboo. Correct me if I'm wrong, please. But what is machine grading? ISO 19624 defines it like this. Machine grading will be understood to be the process of sorting material by means of measuring one or more indicating properties known to correlate to grade determining properties. In the world of timber, we use machines that look like this one or instruments like this one. Not necessarily this is what we're talking about in the world of bamboo. Let me just explain a finding that we made in a research project associated to the development of the standard. And it's around the concept of capacity grading. On this axis, we have the bending moment at failure, or we could also call flexural capacity. And on this axis, you have the linear mass. That is, how much is the weight per meter, or the mass per meter of the specimen that was being tested. It has to be dry, because otherwise you wouldn't know how much is dry material and how much is water. And we found this very strong correlation between linear mass and bending moment at failure. So that told us, oh, this looks like something really promising. Now, this idea has been taken away and tested by other people. It's been tested in Mexico by the team at INECOL, and it's been tested by Effendi Bakhtiar in the Bogor Agricultural University. And we've looked at it for Gigantocloa apus and for Guadua grown in Mexico and Bambusal hami grown in Mexico. And you suddenly start to see there's a trend across species. As the linear mass increases, flexural capacity increases, or the bending moment at failure. We've also found that the trend is noticeable for linear mass versus compressive capacity, this being the force at which it fails in compression. This is for Guadua, Gigantocloa, 3 types of Gigantocloa species. This is the work of also of Bakhtiar in Bogor Agricultural University. Now, another thing that Effendi Bakhtiar found, and that we explored, but he had a bit more success with, and then we've gone back and looked at the same process, is that if you put here on this axis the product of Q being linear mass times external diameter, you get some really interesting findings. It improves the quality of the predictions, and there seems to be, though we need more data on this, that species sort of start to maybe fall into line or very close. So this is for Gigantocloa apus, and this is for Guadua angustifolia. We've got a broader range of Guadua. And for predicted flexural stiffness, we also seem to get a pattern if you use Q times D squared. So suddenly you could predict the capacity properties of culms by just having knowledge of 2 things, diameter and linear mass. So how could machine grading work for bamboo? So ISO 19624 presents the concepts of indicating properties. Those are properties you measure and that are reliable to predict the grade determining properties, which be the properties that you want to create your grading criteria around, and something called secondary properties, which I've outlined briefly. And as I said, it creates the option for strength or capacity grading, and it provides an example. In fact, it provides this flowchart, which says, okay, how could it work? So you still need to check for splits and insect damage, because we don't have the capacity to do that with the machine yet. You could check for taper, bow, and ovality for the same reasons. If it complies with all, you could say that's material of structural quality. Then you could grade by diameter, and then you could check the linear mass, and in that stage, you're assigned to a grade. It provides an example of how that could work. So here you have the grades as before described. Now these are called grade determining properties. So these are the criteria that you need to comply to assign to a grade. So you could have the stiffness and the moment of failure and so forth. And then you have some properties assigned against it. And when I say machine grading, you're probably imagining something really expensive, but we're probably just talking about these 2 very expensive pieces of machines, a little scale and a measured tape measure. So it's in fact very, very cheap. So it could be a very simple procedure, and we're looking to pilot it with a team in the Philippines. ISO 22156. I'm only just going to tell you a bit about what's coming out. We will be talking about round bamboo only. We are suggesting that it's limited to fairly small structures. It's only concerned with mechanical resistance, serviceability, and durability. And Sebastian talked a great deal about durability last time. We are mainly going to work around allowable either capacity design or allowable stress design, though in the annexes we are allowed for the use of partial safety factor design and load factor design methods, load and resistance factor design methods. We also allow for previous established design experience, and we also allow for design by testing. We've created use classes and service classes in a similar way to the Eurocodes, and also to the ISO standards. As Sebastian pointed out, bamboo has little natural durability. This is a photograph I took in Bogota of an example of what happens when bamboo is exposed to the environment. So here you have bamboo degrading quickly when it's being exposed to rain, but this bamboo is performing fine when it's under the roof, which I think complements the point that Sebastian was making last week. As Sebastian said last week, culms must be chemically treated against insect attack and must be protected from rot. We've created, on the basis of ISO 21887, 3 recommended use classes that will require protection by design and chemical preservation. So we fall in line with other ISO standards. We also fall in line with another ISO standard in terms of service classes. One of the things that I think is an interesting innovation of 22156 is that we remind designers that bamboo is very susceptible to splitting and that they have to consider it in design. I'm not going to dwell on this too much. We also talk about connections, and because there's little established engineering data, we provide people with a procedure where we allow allowable design capacity calculation for some fundamental cases, and it provides some guidance for component capacity or complete joint testing. So if you want to go away and test a connection, we tell you how to go about doing it and how to interpret the result. And in Annex E, we have provided an extensive classification of connection types. We also allow for the use of shear walls on the style that Luis Felipe has talked about recently, and say how that can be done. So what's next? As I mentioned, we're looking to create engineered bamboo standards. We want to continue researching, this I speak for myself in this case, connections, shear walls, engineered bamboo products, and capacity grading, and undertaking pilots across the world to be able to take this finding further. We're also looking to create manuals that accompany the standards. At the moment, this is sort of the immediate goal, to create a standard that accompanies 22156. Also, we're very keen to teach structural design with bamboo, because once we have ISO 22156, we think it really has to be unrolled across the world so that the adoption of bamboo is as quick as possible. And we want to disseminate these standards and work towards their adaptation and adoption everywhere. Here's some bibliography if anyone wants to take note of it. And many thanks for listening. Apologies if I went too fast. It's just want to make sure I covered everything.
Yeah, thank you very much, Professor Zhuo. I think it is quite interesting to see from the standards and codes and the certification point of view, like, because we have been working in the bamboo construction sector for quite some time. And if we go in for high-end construction and the projects of high value, there is a critical requirement for standards and codes. Even if we go for some financing from banks, an aspect is being very well handled. The 3 standards for grading, and particularly the visual grading and machine grading is quite interesting, because in our machine grading we have a measuring tape and a small weight machine, so which is quite simple for the practitioners to follow. And and then it is also quite important for us to have the manuals, because many standard documents are quite hard for the practitioners to follow, and it is not accessible for many of them. So practitioner in Africa, practitioners in Asia and Latin America, they ask us, how do we access standards? How do we apply standards? Who will certify us? Who will support us in all those things? So for that, your manuals and then training the people and then spreading the knowledge across on the standards and certification is key. So if we have to take the bamboo sector forward, it is important we have to have architects and engineers who are trained on the structural aspect, on the architectural aspects, which is quite important. So I think your presentation was quite interesting from a point of view, and your recommendations were like some quite helpful for us to take it forward. So I think they have finished the presentations. Now we have to go in for the question and answers. So Mr. Sebastian, who is the member task force, like a member on the bamboo construction, will hand.
Starting off with a question to Professor Zhu from David Trujillo. Could you please confirm what the connections at the corners of the triangles were made from? And do you have examples of the application of the clamped connection, which you talked about?
Okay, sure. Can you hear me clearly?
Yes.
Okay, so my name is Zhejiang and corner connection. So we actually have devised a clamp connection, this one, for demonstration projects. So let me explain the second type first. So actually we have everyone can see it clearly. So at the corner, and we pour some mortar into this corner to strengthen this corner, okay? So this is how we connect the triangles. In these four projects, we own mortar. Of course, the performance of the joint will be better than what we used for the demonstration projects. Okay, I hope I have explained the first question. Answered it. You mean this one, right?
Yes.
Connections, but we did test it in the lab. It turns out the strip on this, how to strengthen this to make this type of joints more stronger. Maybe we can increase the thickness of these terrains because this is quite flexible. As you can see here, it can accommodate.
Great. Thank you very much. That was really helpful. Thank you. Great. Thank you very much. That was really helpful. Thank you. Question to Luis Felipe from Abel.
Sorry, can you repeat your question?
Oh no, that question was for Luis Felipe.
Okay, thank you, Sebastian. So actually, the bamboos are not embedded in mortar. It's the mortar is kind of a skin of layers, so the contact between the plaster and the bamboo is minimal. It's minimal. So no, there is no like such a thing like a bamboo embedded in mortar or something like that. So the contact is minimal.
Are you talking about the longevity of the structure of the bamboo structure? How we protect it? Is that a question?
That was no, that was a question to the second speaker, to Luis Felipe. That was about the alkaline using the cement mortar. So we'll do just to give everyone a mixture. So question for David from Elias. Could you please elaborate on the differences between capacity and strength? Does the term capacity imply a more holistic view of the mechanical performance?
Hey, thank you very much for raising this question, Elias. Yes, well, fundamentally, the difference between strength and capacity would be extensive property. The paper that I mentioned, it's going to skip to the graphs I want to show you, which is the same as megapascals. And here, for example, in this axis, modulus of elasticity, which is expressed in the same units. Now you can see that the correlation is not particularly good. An R squared of about 0.3415. It's not a particularly good correlation when you compare it to the one I showed you of moment versus stiffness, sorry, linear mass. Here I have it against stiffness, but here we could have it against linear mass. And it's significantly better. This is 0.863. So this is now a capacity, no longer a strength, because it's now a value, it's a property of the element and not a property of the material. So the difference lies fundamentally, you no longer treat bamboo like a material, you treat it like a product. And you grade it on the basis of it as such, as a product. Hope I've clarified your doubt.
Thank you, David. So going back to Professor Zhu, one question from Diego Fernando. Which geometric figures could be used and which ones shouldn't be used for structural construction? Professor Zhu, you're muted.
Sorry, could you please repeat your question?
Yes, so this was from Diego Fernando. Which geometric figures could be used and which ones shouldn't be used for structural construction?
What geometric what?
Which geometric figures could be used and which ones shouldn't be used for structural construction?
So you're talking about the form of this, the shape of the structure.
That's what I understand as the question. I think so. Yes.
Okay, I think it can be any shape through design. It can be a dome. It can be a hyperbolic, paraboloid, or it can be a planar frame, or it can be a.
就是任何一个曲面都可以分割成许多三角形。
Yes, we can mesh a free-form surface into a matrix of triangles through design.
Okay, great. Thank you very much.
Thank you.
Another question for Luis Felipe from Loga. Is this technology accessible to everyone?
In around 15 to 17% lower than conventional construction material like masonry or very comfy were around the issues.
Thank you, Luis Felipe. And question for last year they invented with some fellow architects a system of beams composed of 12 thin poles to give them to make bamboo in Chile become a construction material.
Well, thank you, Fran, for this question. Interestingly, I planted in my garden Chusquea culeo last year, and I'll see how it grows. And I might do some my own tests some moment. For the moment, it's very small. But you have the same problem that we have here in the UK if we want to use bamboo, which would be that what's available is small diameter. There is one thing I would point you to for the moment to look at, which I think, in my opinion, is the most successful use of small diameter bamboo, which is the work of Votrongnia. I'll type in the name later on if you want to, which is difficult. The problem, if you think there are other options where you as a complementary structure.
Great, thank you, David. Another question for Professor Zhu. This is from Nick in the making of the triangles for the structures.
Okay.
然后我就把那个 PPT 打开，它是要这个寿命那个是吧？
Can you see the slide, which shows the double ring clamp joint?
Yes, we can see that.
Okay, so yeah, this is the ring, right? So if you look at the top right corner of the slide, you can see we have two rings, one on the left and one on the right. So these two rings can be of different sizes, which is denoted by R1 and R2, right? So R1 and R2, we made a small mistake here. R1 and R2 actually denotes the outer diameter of the bamboo culms. So they can be of different sizes, but the position of the axis of the culms. Is that clear?
Yes, thank you. And what about the triangle, the other connection detail that you showed? The triangle that you connected in a different way with a steel plate?
Yes, yes. I think I just mentioned that we devised two methods of connection, two types of connection methods. So the first one is this double ring clamp connection, and the second one is the bamboo corner. The corner of the triangle was infilled with a bent steel strip embedded mortar. So we can choose one of these two jointing techniques. So for the 4 demonstration projects, we used the infilled mortar infilled technique. We only used this double ring connection technique in our laboratory test, but we're going to work out on that.
Okay, great. Thank you very much. And question for Luis Felipe from Alex de los Reyes. We'd like to ask about the reactions of the residents living in the...
Yeah, is that happening in Latin America, in Brazil, cold very quickly in the night. So compared with concrete and region in Colombia, building with this material that in the beginning they don't use cement, but therefore cement plaster. So you can see it now, and that those houses have already 150, 200 years old. Here in the Philippines, our old, and we are expecting a lifespan of minimum 30 or 40 years. I mean, I actually am quite sure the houses will lot of them.
Work we to frameworks. So ideally, that within pasting, the Philippines has adopted them word for word, verbatim, and made them national standards in the Philippines. Presumably, then people using bamboo might or might not be required to comply with them. That is another step. So it's really, if you want a standard adopted, what you need to do is approach your standards body in your country and say, we would really very much like that you got bamboo in your standards. That's the people you have to approach.
Great, thank you, David. Another question for Professor Zhu. Did you use any structural simulating program for the structural design of either system that you've developed?
Actually, you can use any commercially available software to analyze this structure, but the only problem is that we're not quite sure about the rigidity of the joints because it is not rigid. It's actually semi-rigid joint, so we're not sure how rigid this joint is. So in the future, this is one of our research directions. Yeah, we're going to conduct a larger number of tests to determine the rigidity of the joints that we designed, and if this is a rigidity into any commercially available structure analysis software, then the software will give you the result.
Excellent, thank you very much.
Thank you.
Another question for David. Sorry, for Luis Felipe from Alexandra. Did you also look at the charring rate of the bamboo during your fire testing?
Yeah, that's a good question. So unfortunately, the laboratory don't have that capacity, so we cannot measure the structural integrity of the specimens during the test of fire. So what we did was after we finished the fire test, we get some samples from the bamboo species and we tested. So we see the capacity of the bamboo, and there was some decrease in the capacities, but still the bamboo was able to carry loads that allowed the house to stay. stable and not collapse.
Great, thank you. Another question for David from Nishal. Could you elaborate more on the process by which you decide upon the total number of grades for a species? I think 2 to 3 grades for a species makes sense, but assigning too many might make things more difficult.
Excellent question. Thank you very much, Nishal. I tend to agree. I think the minimum number is 1, i.e. structural grade, and the maximum is where it stops making commercial sense. Because grading is very much about what makes commercial sense to the producer. It's a meeting point between the producer's capacity, what makes commercial sense for them, and what a structural engineer wants to know. I think it's what would make commercial sense. I think probably some 3 grades would make sense. So for example, say we are talking about guava, you might say 80 millimeters, 100 millimeters, and say 120 millimeters. And then the other stuff is so much bigger that you might say it's not practical to create a grade around this. Because bear in mind, each grade that you create is going to have a cost associated to it, because it should be, if you're following what the standard is saying, backed by testing. So that creating a single grade has a cost. On the other hand, the more grades you create, you might have a larger market. So it becomes a tension between the amount of testing to do and what you want to offer in the market. As I see it, this is why piloting is so important, because we want to see what works for each country and the resource. Thank you.
Thank you, David. Another question for Professor Zhu from Elias. What's the longevity of the structures that you mentioned, take into account the roof? How long do you think those structures, the structure that you designed with that roof, how long do you think it would last, and how can you protect and make it last longer?
Okay, thank you. It's an excellent question, and thank you. And it gives us the chance to share with you one video clip that we didn't manage to do so due to a technical problem. Is everybody seeing this video clip?
Yes, we can see it.
So these workers are actually dismantling one of those triangles. You can see in his hand, he has 2 triangles, because this structure was designed to be 2-layer. If this is a single layer structure, then what he is dismantling would be a single triangle. So if we find some parts of the structure is degraded and we want to replace it, we can do it like what the workers do in the video. We can do this. So and so when this triangle was removed, it still remains a stable structure. It is still a structure. It won't become a mechanism, because as you can see in the video, every edge of the triangle is shared by two bamboo culms. So if one of these edge is removed, it's okay. It's just weakened locally and temporarily. It won't become a mechanism, as you can see in the video now. Okay, and we can do this step by step. If there are like 10 degraded triangles that we would like to replace, we can do this one by one to make sure that the whole structure remains stable. So that's how we see this problem to increase the service life of the structure.
Great. Thank you very much. Thank you for the illustration as well.
Thank you.
Another question for Luis Felipe from Frangrio. In Puerto Rico, Bambusa vulgaris is the most common bamboo. We know it's not very resistant. Which system do you think is the most appropriate to build social houses?
Yeah, very interesting. Right now we are doing some tests to determine mechanical properties of other bamboo species in the Philippines. And one of them is Bambusa vulgaris. So there is a lot of Bambusa vulgaris here in the Philippines. I mean, that is the most common species around the world. So you can find it in Latin America, you can find it in Southeast Asia, you can find it in Africa. So it's everywhere. So there's a lot of, I don't want to say myths about the Bambusa vulgaris, but what is clear, there is not too much information about Bambusa vulgaris that you can relate it. So we started with a very simple test that is shear parallel to the grain. Is the first property that we already determined. We test 50 specimens, and it's the same as wild angustifolia can. I'm talking about shear parallel. Not, we have to wait until we test bending and we test compression, but at least for shear parallel to the grain, we are talking about the same resistance of wild angustifolia can, Bambusa vulgaris, Bambusa blumeana, or even Dendrocalamus asper. So I think the myth of the resistance of Bambusa vulgaris is still to be confirmed. And I have a talk this morning, I think, of yesterday with David. So there is also another myth about the cracking and of the Bambusa vulgaris that I don't see yet in the laboratory with the specimens that we have. So let's wait, because I think the main problem with Bambusa vulgaris could be the content of starch that make the species very susceptible to the insects attack. But it's something that could be manageable with a very good treatment process. Maybe if you remove the starch with a current of water, that is what are we doing with our bamboos here in the Philippines. So you remove the starch, and after that you treat the pulse. That will help a lot in the preservation and durability of the material. So, but you can, if you can solve the treatment problem, I'm quite sure you can use that species in a system like Bareke or cement bamboo frame.
Thank you, Luis Felipe. Another question for David from Jaspal. Is there a need of testing bamboo from the source? So, for example, the geographical region, soil testing, strength of the bamboo while it's growing?
Thanks, Jaspal. That's a very good question, a very pertinent one. There just wasn't enough time to include everything I wanted to talk about grading. What we have said in ISO 19624 is that once you've done some testing, that testing results what in the process called initial evaluation is only valid for the region from where you brought your specimens. So you should design very carefully where you are sampling from. So if you say, well, we're going to collect bamboo from this province, try to make sure that you're collecting bamboo that's representative of the variation of that province. So you've got hillside and valley and so forth. And then whatever testing you do is representative of the region. Now, in the past, we have worked on the assumption that if you've tested bamboo from this province of this species, it's equally true that their properties are the same for the same species in a different province. We don't know that to be true. So that assumption is, well, maybe incorrect. So what the grading standard requires is that if you graded from a certain region, that's where you exploit the material from, and then the findings that you have are only valid for that region. So we've called it a source region in the standard, and you don't have to go and study the soil characteristics or anything unless you feel inclined that way, if you want to make it more scientific, to understand which variables matter. But the key thing is that when you produce a sample that's going to be tested, you try to include a variety of things. And it is described in the standard how you should go about considering those variables. That's not prescriptive.
Great, thank you, David. I think we've run out of time, unfortunately. So I'll hand over, but thank you everyone for the questions. Sorry if we weren't able to answer your questions at the end. I'll hand over to Zhuo to close off this session.
Yeah, thank you very much, Sebastian, for your excellent coordination of the question and answer session. So to conclude, I would say that from different parts of the world, it is clear that like bamboo can be like a poor man's like material. In fact, currently it is being used mainly by the rich man, and it comes to the construction sector at least. If we see the major bamboo constructed structures around the world, in India, in China, in Africa, in Latin America, in other parts of the world, it is like mainly used by the rich people in the ecotourism sector or in like some sector, like where we have the attraction as of now. So it is important to understand the aspirations of the people, aspirations of the community, and because the aspirations of the poor man could be to stay in a house currently where the rich man is staying, and the rich man has the aspiration to go back to the nature. So it is an important area which we have to make some focus on. And if we see the travel of the construction sector specialist and Minbar in the construction, we have traveled a path which is quite far, and there is huge path like remaining which has to be crossed, which is necessary to like mainstream the bamboo construction sector. So where it like reach the affordable housing area, and it is been and then it becomes like a mainstream construction like material. So to conclude, we have already completed 3 sessions under the construction theme. The first is on the architecture, the second and third specifically focus on the structural use of the bamboo whole construction, and then we have 2 more specific sessions on the bamboo construction, which relates to the architecture of the use of bamboo engineered products in construction and the structural use of the engineered bamboo products. The next session is on the architecture use of the engineered bamboo products, which is on the 24th of November, next Tuesday. So we would like to see all of you be present in the upcoming session as well. So with this, I want to thank all the presenters, Professor Zuzin, Ivy Trujillo, and OS Felipe for their excellent presentation, and it was quite interesting to see the wide knowledge and expertise they have on their respective fields. And thanks very much, Sebastian, for his excellent coordination of the question and answer session. And then thanks to Kuai, thanks to Jinwai, and thanks to Xinghai, Minbar HQ team, who is working on the backend to support us to organize the webinar session. So thank you all the participants for your time and interest and the questions as well. So we wish you a good day, a good afternoon, and like some good evening, and for somebody good night as well. So see you then. Okay then, bye-bye.
Thank you. Thank you very much.
Thank you very much. Bye-bye.
Thanks, everyone.
So we will have the group photo here. Jiwei, please.
1, 2, 3. Another one. 1, 2, 3. Next. 1,
2, 3. If you turn on so late, we don't have you.